Hello, today I'll be solving a nice integral and then using that integral to solve the Basel problem. Here's the integral in question. Alright, let's get started. We'll start by doing a substitution. We'll substitute sine of t in for x, solving for dx and our bounds, and plugging it all in. Now we will use Pythagoras' identity to simplify the denominator. We'll solve for the cosine term. Again, plugging it all in. The cosines in top and bottom will cancel, leaving us with this nice integral in terms of the sine. Alright, to solve this, we'll start with Pythagoras' identity again and substitute the half angle. Then we'll take the double angle of the sine and again substitute the half angle into that. Now plugging everything in, and we're going to divide the top and bottom by 2 cosine squared. Distribute that and simplify will give us a nice integral in terms of the tangent. And then notice our numerator is exactly the half angle tangent prime, which allows us to do a really nice substitution. Allow u equals half angle of tan. And again, calculate our bounds in du. And lastly, plugging everything in will give us a nice quadratic. Now to solve this, we'll start by computing the square in the denominator, add and subtract y squared, group the terms and factor. Now with the 1 minus y squared term, we'll take the square root and square it. Plugging it in leaves us with a nice addition of squares, which sets up a nice substitution, u plus y equals v, solving for du. And our bounds, notice our bounds are now in terms of y, which allows us to simplify our denominator to a nice familiar form. This familiar form, of course, being the integral representation of the arctangent, which gives us our antiderivative. All we need to do is simplify, expanding out our bounds, and factoring out like terms will give us a difference of arctangents, which will allow us to apply properties of arctangent, which will give us our antiderivative in terms of one arctangent. Now we'll do some simple algebraic manipulation. I'm not going to talk too much over this, but feel free to slow down the video if you need. This leaves us with the arctangent's representation of the arc cosine. Plugging that in leaves us with this very beautiful antiderivative, which is equal to our original integral. And now we will use this to solve the Basel problem. Alright, to get started, we'll integrate both sides of our original integral from -1 to 1. Now focusing on the right-hand side, notice that the interior is just the derivative of the arc cosine squared, which makes this a really trivial integral to solve. Now evaluating the bounds, you just get a nice answer of pi squared over 2. Plugging that back in, we'll now focus on the left-hand side of the equation. We'll start by flipping the order of integration and factoring all the terms that only involve x out. Now notice our interior equation is just the integral representation of the natural log. This new integral sets up a perfect substitution, 1 minus x over 1 plus x equal t squared. Calculating our dx and simplifying a little and plugging everything in will give us similar integral in an even nicer form. We can simplify this by inserting the geometric series representation of our denominator. Now flipping the order of summation, we can evaluate this interior integral using integration by parts. Plugging everything in, we get this very nice sum, and we'll use a change of index to set up our final step. But first, we'll plug back in the right-hand side and divide by 4, giving us a nice closed form for the sum. Now notice that this sum is all the odd terms of our goal sum, so all we have to do is add the even terms to reach our goal sum. Plugging in pi squared over 8 for our odd terms, and notice we can factor out a 1 over 4 in our even terms. So now subtracting both sides by 1 over 4 times our goal sum, and doing a little bit of algebraic manipulation, we have solved our goal sum. We solved the Basel problem. Alright, thanks for watching. This is my first video in this format, so I hope it wasn't too choppy. But most importantly, I hope you learned something new. Bye.